Alrighty, let's see if this works. Right, so, come here, Phaser. Come on. Walking the dog named Phaser. Phaser, come on. He's fine with the leash inside the house. Uh, Phaser, come on. Come on, it's okay. You have to get out from underneath the bed. I know. Just bump your head because I have to drag you out from underneath the bed. Jesus. This dog is timid. He comes out again outside, but he's had a few bad experiences. I can understand. Yeah, yeah, I can see it. Anyway, talk about the engine. Look at our turbine. Fine. Yeah. Here. Here we go. They're basically, but yeah. Engine. Okay. Is going to have these uh, things. Okay. So, you know, I mean, bills is cross housing and pump are both. So they're going to go below, up, and then back down as the engine rotates one way for these arms slash hollow fan blade kind of things, connecting rods. The inside is going to be or area is a screw sort of um, intake area. I'm looking for intake. Efficient, but also not very good at actually helping compress. There's a generic design that's actually fairly good for the. It's a Limi style design that will intake air and push it to the outside centrifugal, or like an Archimedes screw in, out. That does that more or less into the intake fan blade areas that are going to be there attached and rotating to a point. Like not every single one of them is attached to the blades, or right? No, they are. They are for the intake, axle area, and you have to be careful when it comes down to describing this because it's like, okay, so this is a lot that start happening. Things trying to get my dog walking and everything else. We're gonna go on a trail. I'll probably talk during the trail about this. Good boy, Phaser. Yeah, go poopy. You go poopy? No, he doesn't go poopy. Anyways, let's see here. So let's start with the intake, and then we'll work our way out. So intake area is hollow. Basically, kind of looks a little bit like a turbine, but it's not really. It's just an intake with a stop in the back. That's right. Except if I have my way, it's going to be both sides are intakes. We're using a center out design. And like it's all one turbo, centrifugal centripetal compressor design, sort of, kind of. Okay, so if you can follow me with me on that, then you can follow me towards to the end of this whole idea. All right. So first, we're gonna start off that it has to be specifically designed to effectively screw intake, and that's it. There's no cost. I know that's and a pretty good understanding as to why that's the case here in a bit, because we have to get there. But I think you can kind of understand that the exhaust is going to be, you know, at the outer edges of the, hollow fan blade arm things that are kind of connecting rods in their own right. That is correct. They have to rotate alongside of all of the, circumference of these things. But they're in a very specific area. So, as anyone can usually know, not everything has to be a solid piece. Your arms are two pieces, if you don't know, of bone that connect to your wrist, that then have like all the rest of it. And your bones typically also have several layers to them. They're also hollow, but the inside is a metamaterial that produces cells for you. So you have to understand that part. If you can understand that part, then you know that you then can get further with it to where it's like, well, a basic design for the inside of this intake is kind of going to be like this Archimedes screw geometric kind of design that sort of looks an awful lot like a not a fractal, more of a wave fluidic design. It's an Archimedes screw with like in the blades. Kind of looks a little bit more like the microscopic, something like that for our bones. Which is to say that it's like curving in on both sides towards the center, but instead of it being like a perfect screw shape pattern, it needs to be very specifically more of a scoopy design that tends to have holes at the tops where it bifurcates, opens up to allow for the air to pass through towards the center and into the hollow as well for your fan blade connecting arm things. That way it's very strong, and because it scoops up and twists sort of, during that time, it tends to produce a very measurable rotating effect that's got decent amount of pressure thanks to the spin speed of the design and the rest of the mass there. And of course you've got got the whole valve or Bernoulli whatever thing. That's basically kind of what that is. There's pressure here, there's not that much pressure there, but then it's going to seal up. You see, at certain areas, it can go in. At other areas, it can't. You got the valve, you know what I mean? So it's like, it goes down, opens up, allows it to come in, it fills up the chamber that's hollow in the blade, and then rotates up. Then it goes into, and by rotating I mean slides along the inside of the engine housing towards this central area, which is both sides of these fan blades, which have to be counter-rotating. This is also another reason why it's not what you might expect, and why that design seems to look like it's one thing, but it's actually a couple of things for the intake area. Because it has to have a counter-rotational screw that's attached to the inside of that intake that's doing the majority of that work. So anyways, as it intakes, it goes in, and then this will go into that central area. As they counter rotate, it then opens up. They compress against these fan blades with the air that's now there, and you can push fuel through that because it's hollow, and so you can feasibly run a fuel jacket around. That's kind of like lubricating the insides of that screw area and cooling. That then allows for it to centripetally force that fuel based upon the speed. And so, but then you also have the ability to adjust based upon your sort of parameters with a rod that more or less just changes the degree of opening for the nozzle based upon the speed. And that can be a speed of RPM, that is, but that can also be adjusted either electronically, mechanically, or otherwise, meaning passive to active to both. So anyways, it goes in to this chamber, but it's like this will become a little bit more complicated quite quickly. So you're gonna have to follow real fast. All right, so that's gonna compress and ignite, which again, that's just some insulative and some copper coils, and totally possible to make a spark ignition, if not compression ignition, happen there. So, or both, why not, right? Yeah, just needs to get close enough to compress and then allow for the expansion. Now, where's this expansion going to go? This is where the valve went down after that point. It's at its top dead center for the valve, and it goes back down. It's ready to intake some more air to that hollow, but like that also seals it off and allows for an opening into the outer parts of the fan blade. The outer parts are now going to be grabbing on and then being pushed as they expand to the combusted gas, which the first one also is going to do that. It's going to compress, and then it opens up after it's ignited, and then it's going to push it, but then that's going down. It's sealed off, and so it's opening up one direction and it has far less resistance that other way, and then an even greater less resistance the other outer side of the engine, like of the fan blade area circumference. Okay, and then like that is another version of the counter-rotational property of a curved blade. Effectively, it's like zoom, and then it rotates up towards this more expanded area, right? So it's like right, which pushes them open. All right, now we're not going to do any super fancy tricks. This is where it goes into the exhaust housing manifold area, which is of course needing to be cooled. So that's a water jacket, pretty much. It's not that hard to design a basic one, because it's like this is a kind of curved area, but it's like it's doing it kind of everywhere, sort of. You have to remember that. It's like we're not looking for it to really do it everywhere. We look for it to do it every other. So it's like 1 and then 1 and then 1, and so like this 1, 3, 4, whatever, and like a clock here. We're talking a clock. Like these, 12, 3, 9, 6, it does it. And then the other one is 3, all that stuff. Right, 2, 4, and all that. So, and it does it that way. And so it's like boom, 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 boom. But it's like you can burn a lot, but it's like you don't need a lot. This is supposed to be for small little motorcycles, if I'm being honest. if I'm being really, really direct about it. But then I'm a kind of perfectionist kind of dude. You know what I mean? Like I tend to go a little too far over engineer sometimes. And so it's like, all right, so how can I get more out of that? There's nothing saying that exhaust is spent. And there's nothing saying I can't use that to help me rotate the inside. But then it's like, do I really want to do that? And so, yeah, But the point is there's a way to make that turn into a turbine in its own right. You know, the exhaust that's going to either help it suck more in, which is already doing it at the edge of the fan blades, or specifically for my purposes, gain more torque. I'm looking for torque. I'm not looking for it to suck more in. I just want more torque. That's all I give a frick about, really. And I want it to do more torque. So torque is better than RPM for me. Yeah, I'm not looking for super amounts of horsepower. I'm looking for large amounts of torque from very, very small RPM. And so torque is the gas equivalent of a version of extreme resistance to that change of direction that is currently being done, meaning momentum in a rotating or inertial based design. So it's a flywheel battery, kind of to a point. The gas is what resists, not the mass. See, the pressure and gas, heat, volume, is kind of the mass, but it's more the pressure it represents, not the mass. The mass is, yes, but like it can be compressed, it can be moved. You know, it's not compressible, is what I mean. It's not non-Newtonian. It's compressible, so it can be moved back. And so it's like, it's not the mass that we're going to do, it's torque being used to create a pressurized system that's going to be gaining this design torque. And so like that's where the hydraulic fluid comes in. All right, so that's going to rotate a basic design for a torque converter, but it's more of a horsepower converter. Okay, it's a fluidic flywheel basically, but it's going to be helping rotate the intake. You know what I mean? Kind of like a flywheel, but then it's not. And so I have to describe this a little bit better for everyone. So no worries, okay? You're all understandably like, this is what? And it's like, totally get it. It's hard. If I were to listen to this, I'd be like, what the hell is he talking about? You know what I mean? So we're going to talk about that. This rotation is going to create vortexes. And that vortex is energy introduced. As it continues to gain that energy momentum of the travel of that vortex and that exhaust gas, you have to remember that that is a wonderful boom, like just grab and dump it into something. So what that means is as it's rotating up, let's say it's counterclockwise. We're not looking to make it go opposite to clockwise. We're actually wanting it to do a continuation and bleed off until it's just no longer rotating and it's just moving. That's the most efficient. Instead of a smack crash method, it is a slow bleed off method, which captures all of it. Okay, now that's why the housing is no longer an exhaust. It's actually a version of a pump. Okay, which is going to help cool it off anyways. It's going to need to cool that. You know what I mean? So, and all that means is it's essentially a big, ginormous version of a screw that's all rotating one direction, because all of the rotations are going to be one direction, and then they're going to be fed in with the stator, I guess, versions on the outside of the housing for the exhaust ports into this rotating pump. And so it's like that acts like its own baffle slash valve slash, we're all going to just kind of combine our rotations until the very last end where it's going to go and basically try and stop any and all rotation, which that one turns into a series of several blades. Okay, like that's all it will really reasonably be. There's a last stator, and it goes off into this blade, which is like, yeah, I've got a little bit of rotation, and then I'm going to be captured into that rotation, which is actually going to continue moving. Let's say it was counterclockwise, and this is also moving the same counterclockwise motion. It's going to be trying to just bleed that off. And so that's the turbine, Tesla turbine screw design. Like Robert Murray Smith did wonderful video series, but it's like my vacuum blade design is wonderful if you're unaware. And it's like wonderful in the sense that it's like it's producing like this wonderful effect that's kind of like a flywheel. It'll keep it going, it'll make it more efficient, certainly makes higher flow rates possible, but it won't go forever. There's friction, and not to mention you can't always keep the vacuum, and you need a certain amount of wind to keep it going, and it's still very efficient even when it's not doing that, but certainly gains a real advantage once it does. Okay, but if you do a version of this where it's going to curve in, and as it's curving in, it's using the loss of that rotation to create what is essentially a version of a lower pressure zone based upon the fact that this is going to be going up and exhausting around the housing in several areas. Okay, and you have to remember there's a 12 and 6 and 3 and 9, and then there's the opposing. And so like those are your several areas that you've got to work with, and those are all still going to rotate, but they are pulsing like a heartbeat. Boom, 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 boom. And you can basically break that down into several different. You can get up to 4 pulses. Okay? Because there's 12, and so you can divide it by 4, and you get 3 zones that you'll actually compress and ignite. And you don't need many actual fans. You don't need many fan blades. You just need probably about 2. Truthfully, like the smallest version is just 2. You know what I mean? Like you can keep adding more, but more complexity. It's kind of simple, but the point is, it's like do. It's kind of what we're doing. 4 pulses. That effectively, for me, turns it into that rotation is now going to be I already bled my rotation, and so I'm traveling faster through, and like that means it's less dense there, and so like that also helps with the bleed off of rotation for the next one and the next one. And like those blade designs have to be kind of like a scoop slash bent fingers, like feathers, you know what I mean, that have like these little channels at the tips. So as it scoops in, and then it channels, and then it bleeds off, and during that moment, like the opposite side of that blade is already going to be traveling faster, and so like that allows for the continued rotation effect that we're looking for. Okay, but it's while cool and amazing, sure, it is only going to get you so far. Again, if you're burning whatever fuel you can use, pretty much. I don't see a fuel you couldn't really use, regardless of how low grade it was. It's just versions are going to do better. Not so much higher heat, but faster burning. Faster burning is like going to allow for that continuation of increased RPM. But see, remember that torque has to be put into something, and so like that's going to be grabbing that hydraulic fluid. It's on the outside. The outside of that fluid then heads towards the center. Okay, now so just because you have like this one, rotating kind of exhaust sort of thing, which you then have the outside, which is also going to be, the inside. So like, sorry, confuse people for a second, but like I kind of think about it similar like that. Point is, the intake area, engine part, versus the exhaust, rotation, cooling, all that in one kind of thing, is basically all going to add its fluid to the flywheel sort of part. That's the converter. It's the horsepower, RPM, fluid, speed, pressure, all that stuff. And to me, what it means is velocity of fluid at this pressure, meaning it's constantly going at this CFM, let's go with that, of liquid at this mass constantly, and it is then being added into the torquey version of the mass that is the central part. So the exhaust and the central part are then going to combine and add in together and act very much like a very, very, very strong, high torque not very high RPM flywheel, because it has all that mass and all that fluid flow from relatively, slow RPM, like 1200, 7000, something like that, like the range of a normal engine, to be able to get you a lot of torque. And like consequently, it's up to your then transmission. Your transmission will be able to take torque and convert it into, very efficiently, your horsepower. So it's like this has a great deal of energy. That's how I describe torque. It's a huge, huge battery you can dump into RPM like a regular electric motor. So I have this battery. I can then do these things to make large amounts of movement occur rapidly. That's what that is. It's a battery, it's a flywheel, it's torque, it's energy, it's storage. And it's going to keep going. So you have to do the gearing correctly to then take this mass of resistance to that change of its continued this whatever speed, and then make it give you that degree of movement, which is the transmission. Okay, and that's why it's like, it's not the same as a torque converter. It's a horsepower converter. See, horsepower and torque are different. Horsepower is RPM. Torque is not RPM. Torque is grunt resistance to change, meaning like it's not going to stop doing this. It's like a large amount of mass and momentum and inertia. That's what torque is. But horsepower is, I already have that inertia going. I still want to keep adding energy in. That's the RPM. That's how you describe that stuff. All right. So if you must know, it's that. That's how that works. And it's a basic kind of prototype. It's like that. What is that, hollow fan blade thing valve? And it's like, it's basically the version of a two-stroke kind of design. If you don't know, it's like an opposed piston or a two-stroke or whatever they have. Hollow, they have this in the cylinder, this piston head. It's going to rotate up and down. All right. But it's like it seals off at the top. And then it has this combustion zone and immediately exhausts, kind of gets to the bottom. It takes in a little bit of air. It takes a little bit more time to keep it intaking. There's a little bit of exhaust still left over, and you get the picture. It's kind of a version of that, except we're not quite doing it the same. It is very specific, exactingly for valves. The fluid flow of the hydraulic fluid will push it up and push it back down, and the rotation is going to help that as well. For the, right, yeah, for the, and okay, so it's the counter rotation part, which would be tube within a tube. Tube within a tube. Yeah, I know. Not too difficult to imagine. You can put several sections of tubes that are still a full tube, and then still have it rotate. How do you get a full tube? Well, it's the valve. The valve is a part of that tube. So imagine it like this. We're going to take a section of a series of plates, all right, and they're going to be able to slide on each other like a lobster tail, okay? And like, as it rotates, okay, that valve is going to go up and then it'll go down. And it's still connected, but that means it can move and alter. But it's all connected to the same tube, the same rotating, the same sections are still connected to that valve area, which are still getting counter-rotated through the gearing, which is also a bearing. For your engine housing, you need that, basically, to be there. And as it rotates, like the valve then is forced up and then forced down. because there are bumps. Yeah, for the valve, which also compresses, if you don't know. It's on both sides, it's mostly in the wind hollow, but it's like that other side for the other fan blade is hollow. And so like it's draining into that area. And then that compresses it both on both sides, allows that flow on both sides. It gets pushed into the central area and then compressed with the blade shape, angles and so on. And they compress, they kind of slot a little bit into each other, depending on how much compression you want. Mm-hmm. And then you have your spark ignition between each blades, where your spark point is, depending on where it is you specifically want it to happen. Again, that's either by design or meaning your blades, or you can yourself move it around because they can have multiple contact points. It's up to you. That's how you change an advanced ignition. In fact, there can be multiple spots that you can use, or you can specifically just, like what I do, throw plasma. I throw plasma. I always throw plasma. Plasma is easier. If I can create a little bit of plasma and throw it in whenever I want, I get the combustion whenever I want. Throwing plasma is the easiest way. I mean it. It's like, here's this like little hollow tube that's on the leading edge or whatever it is of these arm blade things. And then it's like, as it pushes up, because it's near that tube and it can be in a coil in that tube, I can kind of basically keep creating a little bit of plasma and accelerate it and heat it up and then fire it in at any point I want during its process of compression and ignition. Because there can be multiple hollow points for it to go into, or if you're like me, these are the hollow points. Yeah, like these are all of the little like tubes, right? And it's like, well, no, I can't make it like quite as what you might expect. Okay, so it's like I can throw it in there, but it's like I have to be very specific about it. Like anyone else, you can't just throw plasma in and not expect to get pre-ignition, or have that exhaust go into the plasma. Like we don't want that. Okay, like even if it's a small little hole and gap, it'll go in. Okay, so it's like we don't want that. So you have another valve. It opens. What's a good way to put this? Yeah. Well, it has to open up during and only during, because there's no real port injection. Right. Oh, it's like, remember that whole injection part? There's like a fuel. It's like we kind of need a direct injection / port injection system. You need a little bit of fuel. It helps cool it off. And it's going to be a jacket, and that still gains pressure. But it's like it needs to be able to open up. And like that, towards that top dead center, it's like, oh, I will now be allowed to be activated. I have now, correct, yeah. I have now activated a electrical contact, which allows for a movement, meaning like, depending on when you want it to fire, that's when it'll fire. And for this long, and because it's at this nozzle size and this pressure, because at this RPM, and it can change its nozzle size based upon that solenoid, effectively is what we're going to go with, because it's like a solenoid and a hydraulic ram, because we have hydraulic fluid. Well, slide more than anything. Yeah, right. So it's like it's going to open it up slightly. It's like that's the nozzle. It's going to spray it. It's going to allow it to open for that long. You know what I mean? Right. And you have this amount of timing to do it. And like same thing for the port injection, which is a version of that. I have two because I usually do two. I always like to go lean for port, get an initial ignition, and then fire in a little bit more fuel, because I can increase pressures after initial combustion and increase heat values as a result, but match air-fuel ratios as close as possible as I would reasonably want to, with a little extra, or my style, which is I'm always running lean, because like that exhaust area is kind of helping reduce, as it continues to expand, and I can change the fan. I use bumps. If you don't know, like that fan blade area and the connection is pushing itself as it continues to expand. Like I use bumps. So as it goes in, it's like, oh, I'm in a chamber, and then I have a whoosh, and then whoosh, and then whoosh. And so it's like it's a slightly bigger, slightly bigger, slightly bigger. But it's actually more of a slightly smaller, slightly smaller, slightly smaller. But why is it bigger? Because it's like, well, initially it's very, it's rather like this. This is what I get for push. You know what I mean? Like that initial combustion area. Like I still have other areas that's going to expand into. It's like this. It's like, oh, I already bled a lot of that energy. So if I allow it to expand a little bit more, like in a smaller area or similar area, and then it's like, kind of try and maintain that, I get more torque value, more energy extraction from the fan blades, from push. But like you have to basically scoop it. That's why it's like there's these very specific angles that you have to do that with, because as it goes and bleeds in, it's going to bleed in a certain way, and then like getting the most push out of that, because it exhausts kind of like either in a cone or a vortex or a spin or direct bifurcation. All depends. Like, dog must have pooped in here because I can smell it. Phaser, where are you? Phaser, you went underneath the bed, and he's like a cat. Did you poop underneath there? Come on, Phaser. Okay. Sorry, I'm distracted. Point is, it's like it's a fairly easy, simplistic design. Works rather well. It's all about those bumps. Those bumps are really significant in being able to gain more energy extraction, and you're gonna widen. Like if you think these are really thin areas, it's like no. Think much more 3D. And you think much more 3D. You need to make those areas very energy harvesty, and you're also looking to make it rotate during that, and you want to keep it doing that faster and faster, because that's energy. Well, for us, naturally going to occur. It's going to happen. Like rotation is going to happen. That's just what it is. You have spinning blades that are opening up. They're going to rotate, and they're going to expand. And so you're trying, honestly, to keep with the blades, because of the way they're shaped. They have to be like very, you know what I mean? Yeah, exactly. They have to be very, it's a good way to put that. Fat person armed. Where the Venus or whatever this is, where the trapezoid and tramp, whatever the fuck that is, that is, which I know that sounds like such a fuck you to say, but it's like, it's literally what it is. It's a version of a half triangle. It's right angle triangle, basically. You know what I mean? But upside down, or the point where the intake is, and then the rest of it's off to that. So it's like, that's kind of what the description is. Maybe some of you can understand. But it's like, it has to be very specifically angled and curved and bumped in the internal area and balanced, of course, which is why the counter rotation is so important, to basically keep its spin, I guess, going. Well, no, it's more like happening. Like it's gonna spin no matter what. Like, there's nothing you can do. So you're not looking to like gain and impart energy into that spin. In fact, if anything, you usually try and like reduce that spin. You know what I mean? But it's always gonna happen. So the best method is really to just be as neutral as possible to that spin. You're not trying to add. You're not trying to detract. You're just wanting to be neutral. Allow the boundary layer to be there to allow for that rotation to just continue, but mostly the expansional pressure of that combustion result in a continuation of the energy gain, right? And then you have your exhaust, and it's like, I'm not seeing how the exhaust is going to like be combined, and same thing with this hydraulic fluid. And so it's like, all right, we got to talk about the hydraulic fluid real quick, and we got to talk about the exhaust real fast, and then we're going to go on the trail with my dog, and then I'll probably record on the trail. So we're going to talk about how the exhaust first and foremost, because we're going to be neutral. But there's that stator that's on the outside where the port is, which is essentially just going to be cupping and then allowing that rotation to be imparted and then allowed for more flow, but a loss of rotation, and then that flow gets captured at the end, basically into its, I'm just a slow little, piece. That's the torque value. It's like, so that flow is still energy. If we lose most of that, rotation, because you have, let's say it's just, let's go with just two counter-rotating parts. That makes it a lot easier. So it's like, we're going to go and have all those sides bleed into the main turbine at the rear. All right. And so like, that's where it's going to be attached to on the outside. Just like any jet engine, okay? It's like any turbine or jet engine, it's like it's intaking, it's compressing on the outside, and then it's kind of flowing into this exhaust. But this exhaust is, and the difference between these blades and everything and standard cycles is that we're also adding air in after, and we have to burn what's in the combustion area. So to put it in perspective, we have essentially a being pumped into rocket style thrust. Like it's going to go through that nozzle area. I should have stated this a little earlier, but we have a hollow fan blade and another hollow fan blade, and while that's going in and then it's going to combust, and then like, because it slightly seals, it's like, right. And then we get that combustion and exhaust, but there's still stuff that's in there. And so like that has to be removed. And so like that's also helping push down some of that, valve area. We need that valve to get pushed down, but we have the hydraulic fluid, but hydraulic fluid being pumped around in all these little tiny little areas is annoying. So if we use a little bit of combustion, which that also helps push the rotational effect of the intake. Okay. So it's like all of it's getting used to basically create more rotation. Slightly. We'll get to it, but okay. So that's where the hump is a little different than you might expect. It's more of a really fast up, slow bleed off. And the reason why we want it slow bleed off is because that's what's giving us all of that extra energy. Faster up, higher, faster compression. Slower off, meaning a lesser degree of change of angle, meaning less of any fluid, sudden right angle, smash, and then and meaning loss of energy, and also breaking points for the design. You don't want to break the design. You know what I mean? Like the design will allow for it to continue to ease into that versus like break like immediately off. You can do it, but it definitely does more wear and tear. You know what I mean? And you have a loss of that pressure. With that slow bleed off means it's like there's still a way to gain in that chamber continuation of combustion, but it's a pressurized kind of like that, barking dog or whatever jug with a degree of ethanol, shake it, let it vaporize, that kind of thing, and then you light it and you'll slowly have it burn as it goes through, that kind of thing. That's also another reason why I pump more gas in over time, because there is air there, and that's why I also use port injection. While it seems like it's lean, that lean makes pressurized volumes inside, but then it's still blowing more air that's still able to combust. It's quite hot, like an afterburner, and so I can throw more fuel in, and it's still going to ignite because it's a flame, and so I get thrust as a result that is captured in the exhaust area. So then it's like with the blade angle design that is there, it then turns it, which is why if you look at it from my perspective, that's the, and outside and inside, that like when you look at it head on, it's like, it kind of looks like it's doing the opposite, like that's heading towards the center and that's the outside, that kind of thing, but that's another reason why as it moves like this, and it creates a continuation of that volume as much as we can kind of do it and be very neutral with those little dimples and so on to try and like basically create a boundary layer and really just sort of force that pressure to do a lot of that work from the expansional gas. And the rotation is going to just sort of sit in the middle and kind of try and more or less just be neutral more than anything. But it then extends over into finally it's opened the exhaust area because the tips of the blades are opened, and now the exhaust is there. As a result of the exhaust now being open, like a valve, it then will allow for that rotation, which is the kind of vacuum sort of style, to then go like, oh, there's an even greater degree of vacuum, and then this outside boundary layer gets sucked towards the center as that moves up. That then also allows for that rotation to be captured, essentially scooped, and then bled off quite quickly into the other rotating part at that point for those stator blades and the regular capture the energy kind of blades, right? Which then is going to be another ginormous kind of trailing off sort of thing. Again, that's why it's more of a screw that kind of has these, bends and channels. So, like as it expands as on one way, and as that rotation kind of like goes into effectively itself and more or less just sort of bleeds off to forward movement, gaining that energy back towards directional travel, then the rear becomes I'm going to just capture all of that energy and more or less just try and slow it down as much as possible. We're no longer going to be using counter-rotational. We can't really do counter-rotational as easily on this design, okay, because we need it to go to a fluid flow. Remember, all of that is its own pump. It has an opposing area that it's sealed to, that is a much denser area that is all the fluid. Gas is quite pressurized compared to the dense. Like imagine my quantum thermodynamics theory. It's like we are highly pressurized but very less dense. That is not very pressurized, but it's very dense compared to us. So this can be moved with a lot of high pressurized systems, because like those little fields I was talking about in my, whole down the rabbit hole black hole series on my YouTube channel, then turns into, oh, what do you know? Like this is going to have a measurable effect on that fluid, on like kind of like that, which is a little different. But we're going to move on. It'll still have an effect, but you get the picture. And that's going to basically be a version of the same kind of thing. Like it's going to be moved into a hollow axle tube that is going into what is, for me and my purposes, the flywheel and gearing sort of connection. Effectively, it's a flywheel in its own right. It's a mass. Okay, it's a big mass that's connected to a version of a bunch of turbines blades that can be changed in terms of their angles, but I personally prefer static. But it's going to be inside of that, and then we can just poke it through with an axle towards the center, if we're being honest. But like I'm trying to do the Tesla turbine sort of style, so like it's going to scoop in, and I'm not looking for it to go rotate back in. So it's like that hollow is then going to get added to the rotational effect of the axle that's in the intake area, which is hollow, which is it goes from, it's a good way to put that. We're going to have the front, essentially, just like any torque converter, that rotates in. And then this then means like it's going through and getting basically spun and pumped towards that rear. But that rear is then going to get added to with the outside, because that's a lot more torque. But there's a lot less energy available. And so the outside of a circle gains more leverage. And the center is going to have a lot more leverage because there's a lot more mass attached to it. Okay, but it's hollow in the sense that I need to have things rotate, and I'm still going to have blades there that help the rotation and connect still occur throughout the entirety of its pumped journey. Okay, and then that's where you have to understand the inside nature of several layers. There's like the onions. It's like this is the outside and inside. Yeah, and it's like right. And so like those blades on the inside of the exhaust that are heading towards this funneled point, have to be effectively to the side of the exhaust. But the best design is always going to be directly towards the center. It's fine to have it go off after that center part. But that center part is where we connect to, not so much at the center, actually just slightly off towards the outer edge. That gives us the most torque. Like a CVT, that uses grooves in the plate. Yeah, there you go. You got it. Right. Okay. Yeah. Okay. I know it's a bit tricky to imagine, but it's good to go. Well, to a point. Again, like I'm coming up with it right now. I haven't really refined the design. This is a version alpha, super alpha. You know what I mean? Like it's not done yet. That's basically what I'm trying to get at. It's not done. This is the basic concept. This is how I kind of concept sometimes. I try and present it like, here's my basic building blocks of the design. It's like, this is how you have to design it to get the results that you're looking for. And you have it all come in and connect. Now the inside part, that has to flow through those outside areas, okay, or not outside, but like the middle part of the, I guess we go with the donut again, right, yeah, and then that then has to spread, okay, which means it has to go down and up and across to spread its pressure and flow, but you want to do it efficiently. And remember, there's rotating things there. And so that means the flow is very curvy, not angle. It's curves. It has to be curves. And so you got it right there. It's a diagonal. Whoever might have thought about that, that's what that was. But it was like, it's a version of think candy cane stripes all around the dang thing. Okay, that are then going to go from the inside in 3 different areas, so that way it can then all connect towards that out front side, that then allows for it to give you your intake area. But again, that's not super efficient. You have to remember, it seems like it's efficient, and it is. For a lot of people, it'd be pretty darn efficient. For me, I'm the stupid perfectionist, which isn't stupid, but I'm a perfectionist kind of, hyperfixator in a lot of ways, which that just turns it into okay, so what are we really thinking about? What's going to happen there? And it's well, fluid flow is annoying. Fluid flow is annoying. Remember, it's a pump that's using air intake and compression, that energy to pump stuff around, be efficient, do work, to keep the thing running, but also move you with the extra energy it has on the table. That's all any engine is ever doing. You have to remember that. It's an air pump that you basically create a chemical reaction that you're capturing some of that energy to do work for you. It's all it is. So this is a compressor, which is going to do work for us, which is an air pump that is going to compress and exhaust in a very specific manner, just like any turbine jet engine. But the difference between a turbine jet engine is this will have thrust, and it's all with inside blades in a very compact form fashion. Instead of I'm going to use the blades to basically force it into these little tubes, the blades themselves, or the tubes, the Intake is the intake, and the compression, that is the valves moving and changing their volume, which also allows for a continuation of the burn, which is thrust, and continuation of energy gained during its use, is very highly efficient. Okay, but it's not illegal or anything. You're not getting more than you should. For anyone out there, it's like, where would you get more? And I'm like, well, you're getting more energy because you're putting more fuel in, and there's more air there. Okay, to burn. Like, you don't, this one doesn't take advantage of a piston movement where I can basically recapture some of that flywheel energy by spinning some of that exhaust energy into electricity, and then workable motion energy through the heat and addition of a decomposing source of chemical, meaning water. Decomposes, cools it off, and allows for a extraction of more chemical exothermic energy. So this is kind of what that is. But this is not going to be doing that. Although technically there isn't a thing that says you can't do that here. It's just not necessarily maybe the most efficient, if you think about it. It's like this. That's usually why turbines are so darn happy on high RPM. Like, this one is not going to be. You can go high RPM, but like, it's not really meant to be the highest RPM thing ever. That's not what I'm designing it for. In fact, at all. I don't want it to be that in any way. And the reason for anyone out there that's wondering why, because torque is the equivalent of energy extraction. Turbines didn't extract the energy efficiently. They're highly inefficient. They are kind of, to my version of what efficiency is shit. Like, I would make you illegal if you were that bad at energy extraction in terms of engine you would use. And the reason is simply because I have that exhaust being turned into genuine workable motion. That's heat that I need to use for energy. And while that hydraulic fluid can 100% be continued to be turned into workable motion energy, meaning a spin, that then still allows for the majority of it to be captured and cooled. And it can be quite high temperature for hydraulic fluids, although usually you're not a big fan of that. But it's like, we have radiators. So, there's a way to do that. And we don't need extremely highly expensive materials for a regular turbine. You know what I mean? Like, that's usually very, very expensive to manufacture. Well, now I don't need to do that. I'm not looking for it to get very hot and spin extremely fast. That's not what I want it to do. I don't need that. I only need a combo of regular, high enough temperature, heat, material design, surviving for the strength and tension, all that, steel or metal or whatever we're looking for, coated in a proper insulatory material that allows for that to never go beyond its limits. And the insulatory material, again, will be operating well within its limits. Okay, especially since we don't have to deal with it basically ablating or connecting or essentially doing any massive types of compression. It's still going to do with lots of compression in that one area, but not really as much as you might expect. And it's only for small moments of time, and it's still moving instead of having to stop and then essentially a lot of that. So it's like, it's able to handle ceramically or otherwise the environment better, meaning its use case better. So really cheap to manufacture because you can just dip it and then or spray it on, if we're being really obtuse about it. Like, it's literally like, here's a mold, spray in the thing till it's full with some high pressure, like powder coating or something, and dunk, and then done. Put it down in the assembly line. It's like literally pour this, cast it, make sure, you do your little vibration during the pour for their casting, which for me, that's kind of what I do. It's a low frequency, high frequency, collapsing frequency. It's like a very specific, we're going to collapse it as it goes through and cools. So they're interacting pressure waves that, like any sound waves, like active noise canceling, that energy has to go into something. And so like what that does is basically make sure that it gets rid of a lot of porosity. And so porosity is removed. And then it also, as it's forming, can be used to essentially make a version of, crystalline structure formation. All right, because you can keep it because that energy turns into heat usually. And so like that heat is then like, oh, it slowed down that hot area, or slowed down that, that cooling process in that area, and makes a version of like these structures that are a little bit better at handling and puzzle piecing themselves together as a result, which is why it's better at handling the material, the environmental application, the application that you're going to use it for. That's what I have for one of my designs that I haven't put out yet, but I suppose now I am. But it's like, that's an easy way to just like kind of, because it's just sound waves. I mean that, it's just sound waves. It's like if you have like sand, it's just a vibration, attachment. Low frequency, high frequency, or you totally do it, high frequency, low frequency, pressure waves, or vibrators, oscillators, whatever, can be programmed to do that. So it's like, this is an easy just attachment, and the next thing you know, I've got like a version of quick forging, but it's not really forging. You have to remember that. You're not really forging it. You're just allowing for, and they're still fairly, you can get pretty good with some of it, don't get me wrong. For the casting, like you can get pretty fine on the structures, but you're not going to add in like that much heat. And so you're not going to really do much, but then like try and help align some of it more or less. And you're going to get rid of that porosity for sure. Like you're looking to get rid of any and all of this micro bubbling or anything like that. Like there's little empty spaces essentially. Or for me, what I personally really, really enjoy is slag is removed. Like you can super remove slag. I mean that. It's like a really easy way with very minimal energy and effort to significantly remove any and all impurities other than what you want, because it effectively gives it energy for this density and this material and these pressure waves, and okay, I'm basically going to be able to sound levitate it out of the fluid it's now in by capturing it and taking it out without using electricity, except for the vibrations, the vibrators, oscillators, that kind of thing. And you're not making electromagnetic fields, you're not making charge fields, you're not doing any of that, you're just moving it really well. Just like any, sieve, kind of, you're using the fluid as its own version of a sieve, like that kind of thing. So it's a density thing, but it's like things that are able to, like carbon and iron, actually chemically combine will stick together. But that also means you can create a less dense fluid that then allows for these other materials to sink in and then therefore be added in, that are doping, as the scientists like to call it. I call it essentially like impurity or mixing or whatever you want to really, because truthfully it's all it is. You're not going to allow for any chemical reactions to really occur. They're not going to combine, but they're mixed almost like your 3D printing on a micro to nano scale, almost. Like it all depends on how well you can get that to vibrate and keep itself warm, kind of thing. So let's put it this way. It's like I could put steel and I can add in silicon and some titanium, and that would be interspersed within various ratio mixes, meaning dilutions, with inside of the fluid, and then as it cools down, it'll remain where it's at, and I can then form it to basically utilize that titanium and silicon together with the crystalline structures of the steel to essentially make a much better, lighter, stronger material that handles higher heats, better tensiles, and supports itself far better. Now, granted, that's not the point I'm trying to make. It's like you don't have to do that. You know what I mean? Like titanium and silicon wouldn't be like the best thing, and just throwing stuff out there. You know what I mean? Like that kind of thing. You could do it, but it's like, man, I wouldn't do that. Titanium is a whole thing with lightness. It's like, oh, light means it floats. Why would it sink? And it's like, well, you put it underneath during its, gonna now float up, and then it'll solidify right when it cools, but you need a little bit of pressure. You know what I mean? And so it's like, and it's solid. It's not gonna move anymore. So you kind of flash cool it, sort of. Remember, it's like right on that edge, and it's still able to move, and then you solidify it. Basically, it's not going to move as much, if at all, anymore. Which is kind of a version of, like a particle accelerator firing and doping up a silicon panel for, solar panels. But I don't use it for that. I'm going to be brutally honest. Silicon sucks to do this with. Like, iron is far easier. Like, magnesium, all of it's way easier. In fact, my material of choice, I would probably suggest, if anybody wanted to make this version of it, the turbine that I'm talking about, which I haven't gotten to the middle. I know. Let's just go to the middle, and then we'll get to that. Cliffhanger, I guess. So the middle part, it has, because it needs to be sealed to the intake, because there's intake that needs to happen from that cone on the sides. You know what I mean? So it's like those sides are now going to be added in. So like that has to be an area where there is no, exhaust going to, because if we have it coming in both front and back, that's how that works. Okay. Now, the point I'm trying to get to is that then makes a seal for those exhaust gases to go to, and the return of that fluid as well. Now, it's not very efficient, actually, the way I would like it to be. And the reason is it's doing a lot of change, and it's not really flowing together the correct way. And so, remember, there's always change of fluid flow in any torque converted whatever system, you know what I mean? Right, or horsepower converted system. And that always introduces its own version of lag / kind of behavior that you're not really wanting. Loss is kind of where I'm at. I have loss, fluid flow loss, and pressure loss, and so on. And so as a result, I don't like it. I'm looking for high pressures. I'm looking for greater degrees of efficiency. And so this is why it's a pre-alpha, effectively, like super pre-alpha, basically. It's like I just came up with it today. I had another version which was effectively like two versions of those valves inside of a cylinder that then compresses, and then as they expand, it then also adds some more fuel, and has a slight bleed system to effectively force as it, because it's counter rotating to each other, but also like opposed piston kind of style. It's like as that goes off, that opposed piston sort of like thing, that exhaust flow essentially means that I'm going to shove more air at fairly decent pressures into those cylinders, and then force some more fuel, and then create a version of continued thrust. Okay, that then goes into the exhaust outer area, which is towards the center of the intake, and then the outer shell, and then it's like, I don't like this. This is highly inefficient and stupid. in a lot of ways. Like like I have to freaking get it out, and it's just a freaking pushback. It's annoying, turned into a real annoying endeavor in a multitude of ways. So, um, well, very, 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 very powerful, shitty, and especially when I had to make this heart circle tube thing to basically have it expand. I call it a heart because it would basically expand on the four cycle, boom, 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 four chamber cycle beat. So boom, boom, that kind of thing. So, and it's like I had to, as it slides, basically create little versions of like at various points in the sliding where those are valves that allow for the fluid to flow and basically come in and then get pushed in and then compress, all that other jazz. I have that actually when I was in a mental health facility, that kind of thing. I was working on it and I wrote it down in journals, and I still have them. They're with me in my suitcase, but they're little tiny little freaking journals, and they're probably something that would look like a mad rambling in a lot of ways. If you didn't understand where I was coming from, then you probably would know why it is that like I thought things, because I had spinning piston heads, and like I'm still very certain that will 100% gain me advantages. You know what I mean? Because like if I can spin them and have the right shape on the heads, I gain an advantage. To that mass that's rotating. That then comes back into the arms as it tapers, and then friction kind of clutch adds that spin into and creates a degree of additional fluid, hydraulic pressure, that is, flow for the hydraulic fluid. So it's like, if I can spin these the correct way and then still have that mass inertia, and then that still gives me compression, and then that throws itself forward, and then it, still expands, and then it has that, and all this flow, donut, stuff. You know what I mean? It's a good way to put it is like donuts are now the valve intake manifold area. Like they're kind of like that. All right, and then like there's a vertical, still in out version of that then still flows also diagonally. Right? And it's like there's a lot of that in there, but it's like that's really complicated and honestly kind of annoying and doomed most likely to have mechanical failure issues. So I was just like, this is stupid. Simple. Keep it simple. You know what I mean? So that's really what it turned into. But like that's the start of this. Like really, really super early, like just fucking whatever I can do because I'm bored. I've been in here for like more than a month and a half, 2 months or some shit. Yeah, all told it was like a 3.5, 3 month stay. But point is that okay, so now we're here at this point, which is like a version that's much better than that, because that was using pistons, like actual pistons, and this is no longer doing that. Now we're just using blades, the shape of blades, and the fluid flow, and that creating its own version of pressure and compression, and then like another version of a compressor that's sealed with the hollow blade. But it's like, how do you seal it with the hollow blade? What is this? Well, you know what I mean? Like, right? But it's like actually that one's sort of like an easy design to me. You know what I mean? It's more of that valve that's just gonna like slot in. You know what I mean? Like that's kind of how that works versus with their counter rotating. Right. All right. So you would be correct if you don't have it explained to you, and you're not very good at imagining it yourself and coming up with your own way to have it work. Here's my way of having it work. Okay. So as it comes together, okay, counter rotating style, this valve is really just a simple rotating assembly in its own right that's also being pushed up and moved down. Okay, so it's a gear. A good way to put that is a gear that's going to move up and move down because it slides. But it's sliding, but then it's going to move in a rotational fashion. And so like that allows for things to open and that allows for things to close. As it opens up really fast and then it stays up there for a while for your duration or whatever you want for your version. But mine is, of course, what it is. It opens at the bottom, it then slowly continues. It's going to quickly close, but as it goes up. But I'm trying to keep it open to gain as much as I can. So that's the duration of the valve, which if you're so inclined like me, you can use 2 valves, and you can change the speed of which that close happens or continuation of duration, like a variable valve timing and duration kit for your standard heads on a regular engine for pistonages. There's a lift and duration. It's kind of what that is, and timing is also a way to start that as well, because that can also be shifted forward and moved back, because if you use those 2 valves, it's not impossible to, with just 2 valves, have one of them kind of be free floating and be able to change itself and seal as a result of that, and be altered based upon resistances or areas, like I was saying, for that rod that you can use either passively or active versions to be able to change its degree of continuation of injection for the fuel. Well, all that really is like for the hydraulic fluid area, it's because this has to have that. That's still a way for it to, even though it's sliding in there, it has to have the ability for it to go up and down and have lubrication and all the rest of it. So a good way to describe this is I can do it with 1 valve, really, realistically, but I use 2 just because it gives me a greater degree of variability. Now, because things can roll when they still have friction, all right, there's a point at which friction is not what it's about. It's more about basically at certain points and moments in its time being interacted with. It's going to naturally just continue whatever timing it's at. That's its point in place in the camshaft profile. Imagine that, kind of like it's like, oh, I'm actually at this dot relation to this dot, like top dead center, top dead center. You know what I mean? But then like it then changes its top dead center position for the camshaft and gear effectively. And so like that interaction where it slots and grooves that is on the housing, because it's going to rotate together with, and then like because it's 2 of them, it's just fine to basically kind of slightly alter that and have it show up a little earlier, a little later. You can do it with 1, okay, but like it's like, how does that work? And it's like, well, okay, so if you just use 1 gear, okay, because the blades are going counter on one side, they are all traveling this kind of opposite sort of or direction of travel to the other one in the front. That's the gear part. And so like that gear part kind of like is going to travel along in the circle and still travel just fine, and you have little holes there that are there, and it'll be just fine doing that. And they have their grooves and slot that they'll go up and down in, which the blade is hollow, and that's fine, and it's matched together with the blade. And so the holes open when the blade needs to have its hollow inside, or connecting rod, have intake of air. Right. Now, then it then rapidly moves up like a piston, okay, compressing in that volume. Because air already fills up a chamber that's there, all right, but then also is in the hollow of the fan blade, because that's how it moves to that. And then the seal closes for the valve, then that rapidly rotates upwards, compressing, and it's sealed based upon the housing that's in between, where it's in the center area and the hollow fan blade areas as well. Now that valve will open up, but it will go from this hollow fan blade area, but also across into that hollow fan blade area, and then it's sealed between that because of the gear, okay, the valve gear, effectively. Piston head, like I said, it's like many, many things at once. Okay, now that means it's like, okay, so it's hollow. It's not like a thin sheet. It's hollow, but it needs to be thick like that anyways because it needs to handle compression and ignition and combustion, all that stuff. But what that means is like the outside area, which has fluid flow. Okay, and like this is its own version of like I will allow for fluid flow to pass through. All right, because like that area needs to be its own version of like I'm actually helping create the rotation of the other fan blade. Because it's a gear that is countering it, but like it's also on uh, top of the gear that's a part of the tube system that is the main intake area that needs to rest on the other, attached fan blade area too. So you have 2 points of contact, but then you also have the rear, if you have multiple blades, that's also contacting that one blade too. And so like also the intake of that fluid from the exhaust that I was talking about, as it tries to return, is also its own version of allowing for that fluid flow. So it's another gear that's getting pushed to help rotate the counter rotation blades. And so like that's a way it can move. Like remember, if they're hollow, I can use that to help move fluid through. Because they can have seals, they can be sealed against it, but also allow for the movement of it through the tubes or capillaries or whatever you want to call them, truthfully, because that's all they are. I think these are places where you put this together, and then that allows for, with the right material and the gaps and the shapes, a bearing, seal, and fluid flow that allows for it to go across. That can be very wonderfully insulated or not, if you so choose to allow for it to add its heat back into the intake, which is just fine, if we're being honest, for me, because I don't care. If you're unaware, I don't care. I know that sounds so mean to say, but higher the heat, the better it works. Okay? I like heat. Heat is good. I want heat. Heat is very positive for any engine design if it can handle the heat. It's the fuel that usually doesn't. You know what I mean? And so, like, depending on the type of fuel and regular use, this is the amount of heat you can get away with putting back in. It's typically what that is. And that the radiator is still the radiator, and yes, I could always use my wonderful waste heat generator radiator. Nothing saying I can't do that. And remember, it's just hydraulic fluid with, remember, things are hollow. I know, those blades, I get it, right? And like that's its own version of a pump, like a diesel pump, for the fluid flow of your fuel. But that could also be gas flow, okay? And that's all about timing, okay? So stay with me just a little bit, because we're going to, remember, you're distracting. When you ask questions and then I get down to that, it's like, I need this exhaust thing. Please talk about how this fucking, fluid comes through and, back, right? Like, you already talked about it, right? And it's like, not really, really, no. Like, you have to be really careful right there, okay? You have to be really careful. It's like, yeah, so I said it's like this rotating candy cane design, but it's like, that's just because it's like, there are areas where the valves are, and then there's the outside, which is the housing kind of area that's statically fixed, and they can both go from that to that, and then also the tube on the outside, which needs to be lubricated and given pressure, also to help it act like a bearing between the tubes on the inside where the intake is, and it's like, but I want to cool it, right? Okay, so I need that to be cooled somehow, and it's like, that's getting pushed through the center. Like, okay, so like, it's going to return after it goes through the radiator. We see generator radiators, what we'd use most likely, I would imagine. But point is, again, right, that's not very efficient. It's really not. Okay, like, the bifurcate, the trifurcation, basically, of what that is really annoyingly not as efficient as I would like it to be. You know what I mean? Like, yeah, sure, with the one at the bottom, it's like, oh yeah, no, that's also helping pump it one direction, and then the gears do too. The static at the top is like the least amount of loss, really, but it's also gaining heat because that's where a lot of that exhaust is, and like, then it'll go through, right? And then like, it's getting cooled for the intake area because that's a hollow tube, and then you have the outer side, which has like the blades, but then it's like, that's a right, and so like, that's the axle that's hollow, that has the pump, and then like, the blades is not hollow, that's just a blade, but then you have that tube that's outside, that's the engine block, that has the other hollow area, which is attached to the intake blades, that will allow for it to scoop into, and then the valve, after it's done closing, will then do the result of compression, ignition, combustion, exhaust, all the rest of it. But it's like, that whole hydraulic fluid area sucks. Okay? If you don't understand where my issues with it are, it's like, if I don't push it immediately to the rear where that main high torque, high heat, and cold are combining, which also allows for a driving of greater energies, because it's like a Stirling fluid at that point. High heat fluid that's nearly, because it's under pressure, vaporized, starting to boil, crashing in together with this on the other side, comparatively much more dense, but a lot less pressure, you know what I mean? And so like, you can use the right fan blades to create what is essentially a version of separation, and they want to combine, then they combine, and that then creates a driving version of, flow in the direction that you want, that then also allows for a continuation of that torque up until it's like, now it's kind of basically just pressure. Like, you know what I mean? It's like a short version of a torque converter, but it's a different version, because it's like, the torque converter is my dog. The torque converter has to be not a torque converter. We're converting RPM from all of this into just straight torque. We want large amounts of stoppage, resistance. So what that means is blade angles are no longer flat. They're no longer trying to like scoop or anything. They are just trying to crash, as I talked about it. The rotation and the directionality of the fluid flow from going all towards this one place to going the opposite direction, but in so doing, effectively just leaving it there. Instead of like having it flow faster, we're going to just dump it there. Like, literally, it's like we mixed it and it's like, it's there. You know what I mean? Like, that's basically all it is. Like, that's a really fast pump. really high amounts of torque. It's a huge amount of screws and blades and turbine. And then same thing with this, it's a large amount of outside to in, creating higher and higher degrees of flow that are then going to crash into this. And it's like, then you get like that, it just dumps out on this side. And so you want to drain all of the energy of motion into just basically, this is a reservoir practically. But it will still push it because this is still moving and there's energy being imparted in to that design to make that occur. Otherwise, you wouldn't really want it. You know what I mean? You usually prefer continuation of flow. But if I don't do it over here, then I don't get that torque value I'm looking for. Torque value is very much that pressures combining and then being left to basically just, oh, I dumped the pressures into this huge change of motion that is very heavily resisted that is because of the mass and flow of everything else that's there that's coming in to do this. And so like as a result, because it's non-compressible, all of that mass is effectively tied, meaning the outer fan blades and inner towards the center, and then the intake and blades and combustion, turbine area is all connected to these flywheel horsepower converters, because it's like that's a large amount of flow that is then just being used to just move this, instead of like trying to make a huge amount of mass that's attached to these are going to be small. We're going to attach the mass in a connected fashion via the pressure and the flow and the mass of the entire engine. Okay, because it's non-compressible. It's almost like it's a literal gear, arm, a physical metal contact to doing this. That's kind of what it's like. But it's not that completely. You have to remember, it's still fluid. So, it's just non-Newtonian. I mean, it's not going to compress. You know what I mean? So, no compression, but then pressure waves are quite fast and higher degrees of pressure. You get where I'm going with that. But it's like how those blade angles work. It's like stupid amounts of just, just a large amount of these blades that are going to spin it in together with this other, and then they, it's like these are the entrances. Like here's some valves that open up and then fluid basically spin. Doesn't matter. Point is, people have already done it. I'm very certain of that. But the basic version is like they're kind of a version, again, of a counter-rotational almost design. Like these two areas are valves into these essentially blade angles that are more or less just going to capture both sides and have it move. But then that move is then also attached to this other fan blade that's in, because they're going to trail off and they have to go somewhere. So you got to flow them the right way. So it's like if they're, let's say they are coming from both inside and outside towards the center, but we're going to curve them in as best we can, meaning like a 45, let's say. We'll do a 45. These angles of the blade are like, this is going to come in, and then they're both angled correctly to essentially move that blade. And then as they continue moving, they'll curve in backwards, but then that backward curve is all about just straight stoppage. Like, so that flow, it doesn't matter. We don't want it to really flow. We want it to just be resistant to that change. And so that means a huge degree of blade angle, effectively, very strong blade angles. As it moves in, it's going to have like this another version. That's why it's kind of like a counter rotation, where it's going to go skip off onto that, and then like it's going to impart that motion into a reduction of motion. That's a good way to put that. It's not a scoop. I look for scoops. It's a spin, kind of like a counter spin, more or less. Yeah, blade angle, counter spin, blade angle, because like it's gonna. Let's say we had that 45 and we're coming in, and it as it moves, like any torque converter does, changes its motion, and eventually getting to the 45 with the blade angles it has. But as it does that, it's going to gain a rotational effect, and that rotational effect then has to be stopped by having hit something. It effectively goes from like its flow in its direction, but also, let's say it went from forward, it's now going rear. It's going from rear to up, but in so doing the up motion, it's also have the for the corkscrew fluid flow, like the fluid itself is spinning like a vortex. We're going to have that basically be countered as it tries to go up, thus trading that counter rotation spin and everything to worked motion energy for torque movement, meaning it'll impart that energy into the blades to spin the dang, flywheel torque blade turbine system. But then it's only going to just dump it out. Like it's like, oh, and then I went up, and then it's like, well, there's nothing else, and it's like I'm just sort of more or less sure I have to kind of angle it right, but it's pretty much just static. It's into a reservoir. Sure, there's still some. You can't get it perfectly stopped. I would like to, but it's not really worth it. And then like that just pretty much builds up a reservoir of like, fairly slow moving, but kind of like almost like it's high pressure, right? No, I wouldn't even give it high pressure. Like all the pressure is there in this turbine area. Like this turbine area is where all the energy went. You have to have that be able to do the work motion you're looking for. That's also another reason why it's a lot different than you imagine for a torque converter, because it's not converting torque. It's not spinning fast. It's not meant to spin fast. It's meant to spin extraordinarily heavily strong. It is a 1-to-1 to the spin of the entire jet engine turbine thrust thing that this is. And to put that in perspective, the reason why this works this way is because it is made blade angle, gearing wise, pressure, all that, to spin to a 1-to-1 or lower version of that. Like, and that's kind of what it's meant for, and it's why it's not very efficient. It's basically dumping all of its energy into one flywheel area. And because the flywheel for the engine is the engine itself, essentially. It's a rotating mass that will just be a heavy rotating mass that's very well lubricated and is using combustion processes to keep itself moving as it intakes and exhausts. Okay, but is right? It's a very counterintuitive design for most people. Typically, people go outside in, and this is an inside out. And inside out is more efficient because it uses centripetal forces to do its work, motion, for the compression and everything else. And the fluid flow will still be good enough because as it's spinning and using that motion and work energy, it will up the pressures in fluid flow, but it'll also gain itself some heat back, which is why it has to be dumped back in to the radiator, which then is going to be sucked into the outside housing and the inside, axle pump, respectively. But it's not very efficient. Not really. It's kind of annoying, truthfully. I get it. It's really, to a lot of people, it'd be very, very efficient. The reason why I have issues is it's not gaining the flow rate I desire, the way I want it to. I'm losing energy through a lot of the processes going on, and I'm not using that to my advantage. It's like the blades, the way it changes its motion, the way it's imparting it is all wrong. And so while I was discussing that, I was also doing background redesign work for describing the initial. It's like, well, here's some background redesign work. While I was doing this, I came up with, okay, let's see about why don't I just put what is essentially a couple of versions of rotation or turbines, basically, with inside of the housing. So let's put it this way: so that we have because I hate this freaking pump idea that's in this center, like an Archimedes screw. I hate that design. Like, you have no idea how much I actually do hate that design. It's shit. It is really high static pressure, and change blade angles, all that, but it's shit. I'm not getting any of the advantages of the outside rotations at all in any vain way whatsoever. So it's annoying me. Okay? So, and some people might not agree, and that is a-okay. You are fine and fair to think that, and I might be really, really off on my idea and thought process on that. But again, it's just annoying the heck out of me. Something says no and not efficient and no. So I go, all right, so the outside housing for the engine block and then the turbine and so on, because I have those gears and that area that's there, I can then use that as its own version of we're all going to flow all of that together, and then we'll use the inside turbine area axle as just a straight through pump. Like, it's just going to come back that way, and then that will go into the radiator, and then that will then spread out, because all of that rotational energy is then going to go into a continued direction until the one area where it's bled off, and it doesn't matter that it's spinning at that speed. That's just fine. We're okay with that. You know what I mean? Or that pressure, that flow rate. So, but I'm going to capture it instead where the exhaust starts. Okay. Into this housing area. And so as it continues to go off into this exhaust area, turbine kind of area thing. Okay, let's describe this. So we're going to have flow rates from the front, let's say the front area, intake area, but there's also a rear intake area, okay, everybody? All right. That front area is then going to be doing the trifurcation process. All right, but that's now going to be given the proper blade, pump, screw designs from the gears, the tubes, and then, of course, the exhaust area as well, that are all going to continuously pump it towards the rear. All right, that's fine. Now, instead of capturing it only in one place, we're going to capture it with a version of a hookup sealed system turbine that's within the scope of where the hydraulic fluid is going to. Okay, like, it's going to initially hit this automatically, but then there's still the exhaust, that's meaning from the engine block, from the engine block's tube and gear system, valve, gear, piston, compressor, all that stuff. Then also from the exhaust, that it's then going to hit those blades, and then it's going to trail off with the rest of the hydraulic fluid flow being interacted with for the exhaust blades that are capturing and then putting it into the hydraulic fluid, which is countered to this main, kind of like a cone that's shrinking to a main central axle point. And this is going to be a cone that's going to kind of trail off eventually into just to the side. We're not looking for it to go around the axle. So like that will finally, but it'll cone, and then it'll then have a exhaust area off to the side. All right. And so like that's going to fit with inside of that. And then as it's rotating countered, because that's going to, the axle part for that is going to, rotate, let's say, clockwise or counterclockwise. This one's going to rotate counterclockwise, but this is imparted energy from the exhaust. So that exhaust energy is getting captured and then continued as it slows down for that fluid flow, re-imparted energy, and then widened and so on to continue to try and impart as much of its energy as it can equal to the loss of energy to that axle area, which will, as it continues to flow towards the center, be bled into instead of a curved area, which will still do, but instead of just straight you know like that all that curved stuff design. It has some of that, but like it's mostly just trying to go into a tube that is the basically return line, kind of like our own hearts get like lower pressure systems that'll then pump and then give higher pressure systems, basically similar design. Okay, it's going to take that and then we're going to give it you'll here's an intake to the return line tube, but it's also we're going to effectively curve it and try and have that curve and uh, result of change in motion impart as much of the energy we can from the outside in on that journey, kind of like a Tesla turbine does from outside in, to gain us the greatest amount and degree of advantage possible until it goes into the return lines um, tube, you know. So that then allows for that axle to be more or less insulated. I'd prefer to insulate it from the intake. If I'm going to do it my way, it's definitely being insulated. There's no darn way I want that to uh, basically be used for anything other than like, hey, so this is for sure going to be fairly hot, you know, uh, hydraulic fluid. And so, um, because of that, if I can get that to start from a fairly small to then a larger diameter and allow for, if there is any degree of that, because of that change of pressure, an in part of that heat energy to then collapse, I can gain a advantage by having it pump itself like a thermosiphon into the radiator and bleed off some of the heat. But the problem is the heat, I'm not looking for it to do anything. I don't want it to go into anything. Remember? And so that's where my crux is right now that I was designing as I was explaining that. So we'll go into the fuel flow area and the plasma throw injectors that I'm also adding in. Okay? So the fuel flow is a hollow jacket around the uh, not hollow jacket. No, well, no, it would be. Although we don't have to do that. Sorry, I'm going through a couple of design um, choices. Point is, the initial thing was like, oh, I have this hollow part that's got an intake area that's connected to a sealed ring reservoir fuel rail system inside the engine block. So that way it's always able to scoop it up and then send it as it scoops it up to the combustion chamber and also injector areas respectively. Okay, but it's like technically I can just put it on the blade. You know what I mean? I don't have to have it have a failure point with a seal. You know? Hmm. So like I'm kind of torn, It's like a hollow blade without a hollow blade. How do you do that? And it's like, well, that's it's more of a so you do your powder coating, but your powder coating has a reactive coating first applied that's able to be removed in a particular area, and then you apply a coating over that. But you also have to remember to leave spots for that powder coating. I mean, there's like two molds now instead of just one. So it's like the first mold has these, honeycombed or something like kind of like that area. Then you put the next mold and you powder coat over that, and that creates I remove this stuff that's there with this solution. It could even be just water, and then that has now a very solid, very thick, very strong formed ceramic that's attached to your main bones, like steel or something, magnesium, steel, as long as it's got the correct tensile strength and it's able to hold under pressure and the centrifugal forces and the torquing pressure, even if it has a engine block around the blades to try and help keep it within spec, because of course you still need to have that attached where the exhaust, housing engine block is, to be able to have a degree of bearings and the ability to rotate a lot more effortlessly and sealed in its capacity as an engine. Okay, so but what that means is like you have to add in like the little you know uh, connectors, essentially, that they're little arms that are like kind of like roller bearings that are going to go into the housing that are going to roll and rotate, and it's fine, they'll be lubricated and all that, but that's also why it's sealed and why it doesn't want to move as much. But that's also attached to the ceramic, but then the ceramic again has the bones. Remember, they're not just flimsy thin blades. Okay, like they're not flimsy thin blades. We're looking for fairly thick, but like properly light blade arm things. You know what I mean? Right. Right, exactly. And so it's like you have to have a different type of design philosophy. Instead of a 3D print, it's more of an injection, vibrate, cool, and then put into mold, spray, set, put in other mold, spray, set, heat, most likely because ceramic, and then set, and then dump into solution, get rid of extra stuff. That also allows for your hydraulic fluid, which is coolant as well, and lubricant. hmm Then you also have your fuel flow. But it's like that's why the engine housing was my fuel flow, because I can make a fuel rail that does that. And it's just attached to the arm, which is also a bearing, which also helps it stay in place. And I can also just use it as a part of the blades, which are sealed from the tube versus meaning the tube area that has the other tube right in the axle, so in the engine block that's going to go around it. But is it necessary? I'm like, that's where I'm at, torn. I suppose it'd be like research development to see which one would be better. I feel like the blade part wouldn't be like what you'd want to do, because then you have to start it at the tube for the fuel to be put in, and then like that would be your reservoir, and then it'll suck it up basically as it spins with that. But it's like if it's in a fuel flow and it scoops, it's gonna be fairly close to the tube anyways. So it's results may vary. Do what you want to do. You know what I mean? Like I'd say the scoop design works pretty darn well for me, but that's also another reason why it's like that's where I can kind of poke into it with the hydraulic fluid as it flows through. That hydraulic fluid with a solenoid in the engine block can be activated like a valve to allow for the flow at various times and close at various times. But it's allowed, because of the electrical contact, to be activated via the motion of the compressor valve gearing system that is going to slide on the sort of like a bell curve, but it's more like a rapidly goes up and then trails off slowly and then does it again. So it's kind of like a heartbeat. That's why I call it a heartbeat, like a dun-dun-dun, right? But it's like more of a rounded off hump, if you will. So that allows for that flow of the fuel to go in, and then the contact then allows for the solenoid to pass the hydraulic fluid through to allow for the injection, meaning the hydraulic. I mean, that's a throttle body. I'm not really looking for a throttle body. And I'm not looking to push it, because I'm looking to hold it in and then allow it to go in, which is why I thought throttle body. Ah, but it's like sliding it would be easier. You know, like that, like just you know, right, right, because you only need to have it active or not active or active this much, which is why it's a rod, is how I like to call it. So the solenoid allows for it to move that little piece that's there. That's going to be, again, it's going to be sliding with the um, blade because it's a ring valve that's sliding, and it's of course attached to, you know, all the rest of it. Like that's a rotating up and down gear valve compressor. Okay, so like as that rotates and compresses, and you know, all the rest of it. But like, there's nothing saying that that's every bit tied to our intake. Right? And that can be mechanical, passive, like it's statically fixed to this, to active, which is like, oh, I can have it consistently like this, and it should still flow fuel in so long as it's still a good valve. But what it means is I can also open it up a little bit more, or retard it a little bit more, or open it up again, that kind of thing. Instead of like I only get one, I can now get two or three, or continuation of fuel flow, which is where the burn happens. That's why I run lean, and it's like I can have multiple spots, meaning the ports injection, you know, for the hollow area where the gear is. So like that gear is hollow, and so like as it opens, it goes up into that other blade, but there's no chamber for it to go into. Okay, and so like then it goes and flows over into the other hollow blade. The other hollow blade is now filled, and then it's like by that point, it now is trying to start traveling up, and I can continue the duration and fill up that chamber as well. Okay, and as that chamber is filling up, and this then closes. Okay, now that is then, because of the blade angles and shapes, is compressing and getting basically made with these little ribs that are going to get really close together to essentially compress that fuel and air, and like create a area where we have a gap, but also high amounts of compression in that one little small area. And that's a spark, or for me, that's a hollow area, because I can do that. It's not impossible, because I just showed you how to make a hollow blade, you know. Which allows for the fuel and air to flow through. Now, granted, again, these, I'm trying to also make the metal part, most likely is what you'll use, blade, also be hollow, which is also possible. It's just a mold that you then put this in, this cast into, that has its hollow part for the metal part, that then you can then use the other molds to build on top of and remove respectively. Really fast, cheap, quick, all one area manufacturing. Okay. Um, right. No, he already described that. Yeah. So, and then for any commenters out there that might comment, you know what I mean? So then it's like, all right, so that then can be gained an advantage by allowing for the inside of that mold to be an impression, or opposite mirrored, for the fuel to be very, very wonderfully moved through and gain a advantage for its curve and flow and fluid pumping action and pressurization action, as well as for the air intake, fluid flow, compression, and pumping action, and sealing action, and all the rest of that, right? Because we're still allowing air to go towards the center. Like, that's why it's like allowed from both sides. Like, this is really kind of meant to be more than just two, but we're describing just two here. So like, that's really just sort of a different sort of design. Right, yes. Right. But that fluid flow is now in an engine block, which is the fuel rail. It also helps cool it, but it's separated from, especially with hydraulic fluid, okay, which is this engine coolant, but also, right, um, it's not just engine coolant. We're looking at lubrication. We're also looking at the separation, because we also have stuff that's separated between that, and that can be very much a vacuum, especially with mold designs that we can make, you know, and just pump it out. Like for me, I'm like, oh, I'll just form it with air there already, and then I just pump it out and seal because that's easy enough to do. And then, right, and so that allows for a insulatory, and then I still have the uh, hydraulic fluid also act as an insulational barrier to the fuel, and then the intake itself as well, which is really a positive if you ask me. All right, and so that positive is nice, okay, but for me it means I have the ability, because I'm leaning it. So it's like as I'm injecting it, where the hollow gear valve and compressor piston head area is, it's like, okay, so that flows through and it's going to be lubricated by that uh, hydraulic fluid, as well as allowed to help pump it around and flow through from one side, okay, and then it'll go through that way. Basically, it's like on the outer side, so it's like it's going to skip through and skip through bypass. It's connected, okay, so it's got like indents, and like those are where it's kind of like bearing sort of and connected area is. That's a reason why the fan blades are moving together, kind of, right, right, kind of, right. I have to describe that. So mm, they are tied to all the other fan blades. It's not just one fan blade. You have to remember there are as many or to as little that will feasibly work. As far as I'm aware, you can do easier more to a point. Okay, like you have to remember, then you don't get the trail off as much, but then you get more combustion cycles versus, so instead of elongated hump, you get a spikier graph, you know? Yeah, which is a bit rough, okay, on the materials that you're using this for. And so, like, typically when you think about it, it's like we really probably only have about 4 blades to maybe 6. Okay, and so like 6 is probably an easy enough way to describe this, but as they rotate, sure, those fan blades are technically not there, but that's also where the sealed system is, setting up to allow for the other fan blades to be intaking during that time. And then it connects and it seals. Right. And then it compresses, and then it does its whole thing, continuing to seal, and then allows for the intake to begin again. The whole system and process works, you know, but the more blades and, the diameter, meaning sizes of the gears, piston head valve thing. See what I'm saying? It's like it's a very many things in one component. You kind of need to have like a few different things together to make that work. Because it's doing multiple things. But like that on the outside, the hollow, fluid goes through mostly just one side. But that's why it's a circle, and that's why it's like, oh right, it doesn't go through the other side, because that's fine. We don't want it to return. We're looking for it to gain that advantage of that rotation to basically remove that boundary layer of loss of energy. But then it's like that's also a pump right there. You got it. So like if you allow it to flow through, but then also pump while it's going and doing that, because it still has rotational energy that can impart, then you can use that to your advantage. And you still have the exhaust sealed area, which is going to go up to there, and then you still have the exhaust manifold area, which is still also going to go into that as well. Then you have the tube, which is like the tube in the tube. So it's like there's a couple tubes. So you have the central axle tube, then you have the intake area fluid coming in tube, then you have like the housing engine block, and then we're in between the blade, other blade that's going to be like this thin film slash not as thin as you might imagine actually. It has to have the blade rest on a gear that allows for it to spin counter-rotationally to the main tube body housing that is all rotating one way, and then this one's going to rotate the other way, like a ring, but then it's connected via those valves and that gear, and also the fact that like the housing at the top, so it's kind of like its own version of like, while I'm multiple sections, I'm all kind of one kind of thing. So as a result, it's going to take that hydraulic fluid and send it to the rear. You're going to capture as much energy as you can from that sent energy from the hydraulic fluid. Okay, alongside of, yes, we do actually kind of need to add in the axle part, the gear axle part. Okay, so like for anyone that's like, wait, what? It's like, well, it's kind of like a turbine within a turbine now. Okay, a jet engine turbine within a turbine is essentially what that's going to become, because it's like the intake side, remember, because it's a circle, right? And you have the rear intake and the front intake. You want it all to travel one direction because that gives you the greatest advantage for all of that mass and fluid flow to be captured. But you're also going to have that attached to the axle that's attached to that tube, okay? Like that's going to be a part of your flywheel. And that flywheel is going to also be getting energy imparted into it from that exhaust and the hydraulic fluid. Not the, well, that exhaust hydraulic fluid connection, because there's a seal between that two. And it's all one kind of piece, but that kind of rotating seal kind of thing. But then it's like those side intake areas are also where that cooling is not really something I want. But like we could do it, but again, it's like I want to insulate the shit out of that. Anyways, I'll get to it. That's going to intake air for the rear part of this turbine area, which is a center out approach. Okay, so that's coming in. That also is being used to help drive some of that intake towards the sides, but it's really just intake, empty space, more or less. But you can always kind of get a little bit extra if you know what I'm saying. Like, good way to put that is I can, on that rear part of that turbine, have that spin and try and suck in air itself along with the front part of the tube, even though it's coming, for its return line to its radiator, okay, from that center axle part that's hollow, okay. I can also have that still intake more air by having, fan blades or, a cone and section that intakes from with the Bernoulli's higher flow rate principle that then with blades that effectively kind of like, while they suck in and then they curve in and then they pressurize as they get closer and closer and bifurcate the air, kind of chopping it, and then more or less holds it with high static pressure as it flows much faster towards the center, and then kind of the same thing for the rear. So that initial intake part is just like a supercharger because it's only running off of the main body. And this is the turbocharger because that's, well, kind of connected to the main body, and so it'll start it immediately, and it all has to run together. Okay, it then also doesn't fully start all of itself completely immediately. It will then get picked up by the exhaust that will have it spin faster. And then that can also be added into, but not really that much. That's where the heat is that I started using. I want it to be insulated and do nothing until we get to the intake supercharger part, because that's still a lot of heat, and if I can maintain that heat, then that can then expand and impart energy and rotational increased energy into the intake of the inside of that, because it's like that's the hollow tube, but this part is going to be connected to that, and like if I allow it to expand, then that can be captured, and then it'll be sent into the radiator, okay, which will then cool off, but also gives us pressure, okay, because there's an expansional part, which is then cooling off and condensing, and so like that's a thermal siphon effect that will then allow for itself to be captured and caught by the intake blades of the front part of the engine housing, which are then going to pressurize it as a result of the pumping action of the air pump coming for the air coming in and combustion happening, and then energy extraction occurring and being dumped into the rotation and the fluid flow for our hydraulic fluid, which means I'm capturing a very large degree of the heat energy into rotational energy to suck more air in, but also more torque value for our flywheel, area for the clutch and everything to attach to. Okay, which still has a direct connection as well, but then will spin faster on top of that direct connection, which is just a what would you call that? As it for a gear? Yeah, no, like right. Because it's like we don't want to just use the hydraulic fluid. We want to have like that solid axle, right? But it's like we can always have that have faster spin rates, or perceived torque. And remember, spin turns into torque when you do it correctly. Okay, and so a faster degree of spin can then be used to impart itself into that inside diameter tube torque area with the connection of a gear. Okay, and then that will allow for like that faster moving spin to basically be a geared connection to the central axle, which will then allow for that gear, or that axle, sorry, to be able to receive a very high degree of the torque from the exhaust, okay, into workable motion energy for our flywheel. All right. While still allowing for some air intake in part, if you wanted to do that with a super turbocharger setup automatically put into the engine design itself, the get-go. Okay, and then the radiator really can be anywhere. It doesn't have to be in front of it like normal engines are, because like I don't want it to really impact my engine's performance. You know what I mean? And so there's nothing for me saying that I can't utilize a just tube, a bendy tube instead of a hard tube. It goes over to there instead of over to here. It's like I can do that. So like we're talking motorcycles, so it's supposed to be for motorcycles or bikes or something like this. Something that's reasonable, to a very significant degree, to not have to worry that much about like where a radiator is. Like typically you're like, we want really fresh air, and it's like, yeah, I mean, yeah, but like, I can air cool this. If I put like, for a small little tiny engine, I can just put some fins on the outside of the engine housing and just run that return line to the outside of the housing and separate with an insulation of a vacuum or a couple vacuum walls, and then that's my coolant area by having like that be the radiator surface area with a bunch of you know um, hollow fins effectively that are all going to allow for the channeling of that you know okay, so it's going to go down, it's going to go up, it's going to go down, back, that is, and then it's going to go up again, and then it's going to run through the front and then into the intake area, respectively, which means it's going to take quite a while. But like, those are just thin, it's a circle, thin kind of like sheath of the hydraulic fluid, and then it's going to go into a bunch of spiky channel fins, kind of like a vapor chamber. You know what I mean? Which, because it's now allowed to depressurize, then it'll vaporize, and then it'll go through that, still kind of as a vapor, and then cool off as it's moving forward, condense, and we just need the fins to kind of like go from wide to small in the front, so that way they're denser, and so the pressure is better, able to be used essentially to cool it. And then I can put a couple fins towards the front. That allows for the separation, kind of like the bumps on the whale, fin, and then that separates the airflow to move around it very efficiently and be very efficiently cooled. We're not going to gain that heat back, but I'm okay with that. Truthfully, I'm okay with that. I don't really need all that extra electricity. I mean, I have to put that electricity in something. So like the waste heat generator is an electric generator. It's not a workable motion movement generator. You see what I'm saying? So it's like that has to be put back in somehow. And it's like that's batteries, controllers, electronics. It's just, while not super complicated in a degree, in sense, it's just more work and more stuff to be done. Whereas this is just like mold, pound, put it in, some bolts, some gaskets, put a gas tank above it, put some hydraulic fluid in it, and Bob's your uncle kind of stuff. You know what I mean? Yeah. So it's like, oh, it's done now. It is air cooled, but it's also liquid cooled, but it's also the engine's lubricant and coolant. And then it's also, yay, you know what I mean? Like small, compact little thing, that's got side vents, or not vents, intakes and front intake, which can be very well put together, right? That allow for that to not interfere with the cooling, because the cooling will be on the outside of that. And so like that's that one whole intake, which will split it to the rear, and that'll be matched for the size and diameter of those holes to the size and diameter of that add-on for the front as well, with the intake of the air, which will help compress it on the outside and still the center. And then the rear is also allowing for it, even though it traveled a distance, it's going to curve in. And those blades basically allow for that intake center to be continuously added to, compressed, sent to the intake and combustion cylinder blade area, respectively. You only really need maybe 2 of these blades to really kind of get there. This can be really rather small and compact as a result, and then I can then put that into a much larger, form factor, like for the intake, because of course more efficiency. But then like I only need those blade angles to be so long, you know what I mean, like, or the blade result of combustion power area, cylinder. It's not a cylinder, but whatever that is, right? Yeah, and then it's like that area, that donut area, really, where it's sealed and it's doing its work for the engine block, only needs to be so big. You know what I mean? Because it's like there's only so much distance you can really travel to have that. And by the way, while it's adding its exhaust energy into everything. That is also pushing it into the intake design for the next area already. So like it's almost like a two-stroke in that, or one-stroke constant, never-ending intake exhaust. And while the exhaust is still like being used as energy input, it's still intaking and actually going to probably start another intake and or even combustion, depending on where it is. You know, like how close those blade, uh, you know, uh, degrees are. Meaning those are the degrees on the circumference of that tube. So that's kind of like how many of those fan blades you have is really what how many power strokes are constantly going on at any one time, because the exhaust is still going to keep pushing to keep giving you energy along with the hydraulic fluid. So it's like all really rather compact and very, very efficient for what it's worth. And it's being used to intake for work energy. It's being used to use all of that also for work energy. But like you have your intake pretty much taken care of. You know what I mean? Like you don't want to go past a certain point for intake. You know what I mean? And it's insulated, so you're not going to have combustion within the intake or any knock or pre-ignition. You have your cake and eat it too. Oh right, I never did the plasma injectors. Thank you for reminding me. Totally forgot. Yeah, that's the tube area. So like that there's a hollow tube area that's wound around. And I mean, hydraulic fluid is sometimes conductive, oftentimes not. It can really depend on what you want to do. So like I'm looking for not conductive. And not conductive is often not super great at turning into a vapor. Okay, and so like that's the balance, you know. So it's like if I manage to make it not conductive, but meaning insulative, or at least neutral, you know what I mean? Right. But it's like I can have a engine block component that sits in there, and that's a version of I just need to get a little bit of air, which we have air, that's fine, and put that into a reservoir. I compress it quite a bit, which gives it heat, and then I can significantly uh, just make a very significant amount of electricity, more or less, occur. Like I'm looking to plasmify. And so plasma is like usually not done that way. And so like a spark injector with like the coil and all this stuff that I'm talking about for like a, engine with a piston engine is going to be a little different to this. So like it's going to be like a bump system. So it's like it intakes in a rather significant chamber. It then slowly rises up. That compresses that chamber. Then that doesn't have a lot of heat. Okay, and so it can have a lot of heat, but like it doesn't have usually that much heat. And so like really that spark area is a bunch of different gaps that we're then going to also have a bunch of those electromagnetic coils, which that gap is now along small amounts of plasma is there because spark has occurred and that's plasma. Then I am exciting the air in that plasma to expand further by doing this, and then that then opens up into a chamber that is in the hollow fan blade that is going to race up into uh, one blade area. I only use one blade area. You can do both, but I only use one because like, that's just a lot less complicated. And so as that travels up either the leading edge or along the blade or in the inside of the blade, remember, it's insulated, but it's like I can always make that um, go through the engine block, even where it can be a hollow copper or some other type of tube, or I can have it go through the fan blade, which that's for me what I prefer to do, because then it's like, oh, it's a plasma that will be insulated and hot and then basically squeezed and centrifugally compressed and centripetally compressed as it has the rotational and the vertical from out or inside to out, and then from a forward to rear direction. But that forward to rear is centrifugal because it's using the rotation of the uh, design to create the movement from forward to rear, and then the up is the centripetal, which causes a accelerational movement, and then I just need to have it survive. And since it doesn't need to survive for very long, as a travel, component, like it doesn't need to get very far, the plasma that is, then it's able to fire into again just the ring kind of valve system that can be allowed to essentially have it pass through, uh, which right is a part of the rod kind of thing that's attached to the engine block area. So it's like that then allows for it to pass through with a bump, essentially. The rod changes. That can be automatic, or it can be meaning passive, and it's always going to happen at this point, or it can be active / passive, where it's like it's always going to happen, but like you can kind of move it a little bit because that bump can be moved. So a little bit before, a little bit after, that kind of thing. Right. Which just allows for a valve to be opened. That's what we're looking for. So then it'll travel up, and you can time it based upon its travel distance. Yeah. Okay. Okay, and then you can always add more plasma or reduce plasma, all the rest of it. Based upon how much energy you want to put into it. It's like, where are you getting this electricity from? I'm like, anywhere? Like, I have a ginormous rotating mass. There's even heat. So, like, this is an axle. There's a rotating axle. There's some copper coils and some magnets. How about a battery here? There's an alternator, I guess. Then I can always be a dick and be like, so you remember that radiator on the outside? Yeah, no, this is just like a shell radiator that we're going to stick with the gaskets and everything. It's the same kind of radiator concept, thermosafe and blah, blah, blah. But it's got little fins on the fins. It looks like a sun kind of like thing. Spike. Makes this fluid go, and then comes back in as it cools off. Tends to travel from the rear to the front. You know what I'm saying? Cools off. Does its little doohickery with some piezos and some linear generators and nitronols. And I'm sure we can even add some tubes where the expansion of the gas then spins some stuff. There's some I don't know, coils and some magnets inside the little hollow, tube thing. Might as well do that, right? Mm-hmm. What? It's not wrong. I can totally do that. I'm just letting people know. It's like, it just seems stupid. It's like there's many ways to gain the energy back to do this. It's all up to you. I'm just kind of angry about that question because it's like that one seemed like you really probably could have known how to do it yourself without me in any way getting involved. There's like several different ways there to do that one, but let's just go with like a tube within a tube, where like that, expanded fairly not lost, because it's, of course, whatever is pushed through that insulated vacuum area is going to go into the now expanded vaporized hydraulic fluid, which is going to be a part of that design, kind of like steam, but it needs to be lubricating, so that kind of thing, right? And then gets cooled off, right? And then like that's going to be used to impart energy at first, but it's insulated. You want to make sure it loses as little energy as possible. And while it's connected with the gear, then that's then able to spin and impart its energy further to spin faster that super turbocharger, like the rear and the front, okay, respectively. But this one's getting help with the exhaust hydraulic fluid. This one is not getting anything except for the expansional part of the hydraulic fluid. Steam. Well, we're not going to use steam, but kind of like that. Yeah, vapor. Yeah. And then like that's going to go finally into the exhaust area, which is this going to spin like what, like small little tubes? Yeah, pretty much. I figure like small little tubes would be good enough, and like it'll cool it off most likely by like a certain distance. And so like let's say it's a full 3 to 6 inches of distance, and then you'll have a larger area and then a smaller area, and tapers and fitting within inside the scope of like the housing it's going to sit in. But I need that to also help expand further, by like a heat sink, then the surface area that it will dissipate the heat in. So like that's going to be its own version of a thermal siphon. I might as well, right? It's like, right, yeah, that could just be a lower pressure water. Yeah, I figured, like, right, yeah. Because it's like, oh, that's going to be fairly hot, but it's like a lower pressure water would probably do just fine. If not water, then whatever it is you really reasonably want to do in terms of whatever fluid you want to use. But, right, because then it increases surface area and the speed at which it will dissipate the heat. Because it's like a pump. Yeah. Right, and so it'll go through the tube, it'll dissipate into the housing, which is going to be resisted through it's going to be a magnet. It's going to be a hollow magnet. That's literally what that, for me, is going to be, where it's like we're going to put together a couple of magnets in a housing, effectively, and then that allows for the, rotations into the copper coil, which will be jacketed, which is why water is probably not the best move. Okay, but like that fluid, but it could be water, honestly. It really depends on what you want to do there. Because you can always insulate the water. I mean, the copper. Right, which you probably would be doing anyways, most likely. Ceramic, I guess, then would be a decent way to go about that if you wanted to do that. Anyways, but that will then impart its spin rotation into that, and like you'll get a little bit of electricity back from this. Then you still have the rotation of the axle and the hydraulic fluid and the expansional, all that. So like we're getting the expansional, and then we're getting the hydraulic fluid, which is under pressure and cooled fairly well by the air moving over back, and then pressurized, and it's flowed much faster towards the rear. And that rear area is going to be able to still give you just a literal like gear connection or any kind of like standard connection that you might want to do for like, it's still a plate, with like magnets and some coils. So, that probably will give you some electricity there as well. And it's cooled, so, that will probably be good enough to provide a degree in a battery or something similar of storage as a capacitor, like a battery capacitor system that can then be dumped into the spark plugs with some standard coils and, all the rest of it, because this connection in the gap is good, and you have several areas where you can create a decent pocket of multiple kind of little spark gaps, and then like excite it, and then really heat it up, and really give it the old beam juice, as they say, and make a plasma, and then throw itself in, making it a lot easier to. And then, right, you can delay or increase the timing in where the valve opens for the plasma, and then it'll go and then get sucked into the chamber. Which sucked is not really a good way to put that. It's getting forced through centripetal centrifugal forces. kind of like a compressor. So it's like really, because it's very hot, and so like it's quite higher pressure than what's inside that chamber. So standard fluid flow dynamics. Like saying that's low pressure. I am much hotter and higher pressure than you. I'm going in. No, okay. Then you had a valve system, and it's like, well, yeah, no, I do, but it's at the base of the tube, and it's like I can always kind of like just use that, and then I can use a basic electromagnetic if I really want to get really into it, which I don't really necessarily need to because it'll still do that. But it's like if I really want to, I can then just fire the plasma with like a coil, like just put a couple copper coil or something like that on either in the inside of the hollow or just in the engine housing, and then just coil railgun it into the chamber, so which there's a reason why it's like, why don't you have moving parts on the blades? And like, the blades, I don't want any moving parts. The blades, I never want moving parts. I literally hate moving parts on these blades. It's like, why? And the basic simplistic answer for me is those are difficult to move. I can do anything in the engine block in the housing. You know what I mean? The blades are hard to deal with. Like if they're hollow and easy to just move fluid through, that's simple, easy. I can do that. You know what I mean? Like especially when it's like I can have the right little pieces that are in between. And so let's put it this way: the engine block can still sit inside in between. Remember that the valve that's there is sitting in between these two areas, and like the hollow allows for it to basically move through this rotationally and not interact, meaning it's going to get the hollow part of it coming in and then opened, and then like all the rest of it, and so like it's going to be just fine going through that. Then you can still have a static fixed area in between that chamber, okay, that allows for you to stop the plasma and fuel injection respectively, depending on what you want to do, okay, which is like its own version of a rotational ring gear system, valve. Like I can have that at different, not going to be in the same points at that chamber, okay, but it's like those, yeah, you get it. Like those designs then mean it's like I have several different ways I can play with this. I can either do it at the tube intake area or at the blade area. And for me, it's like the blade area is annoying. I don't want anything to be anywhere around that. I'd rather have the blade just be its own version of I seal you off, and then it immediately comes out because it's much more simplistic, and the engine block housing is a lot more simplistic as well, and stuff isn't in the way as much, and therefore efficiency is gained because I can do more with like less basically getting hammered with heat that isn't supposed to or needs to get cooled down, so on, so on, so on, so on, so on. So it's just more simplistic kind of stuff, but there are ways I suppose you can get around it. Like again, this is all things people can refine and do. It's like the basics, pre-alpha build. You know what I mean? Like it's all it is. It's a intake area, exhaust, intake center, compression center, ignition, and then exhaust power stroke all in one. Which then the exhaust port is now like also being captured as energy and cooled, which is fine, but then they also have a thrust by adding some more fuel, and the air is still going to continuously be lean, and so adding that fuel the right way then continues to add in that heat, which continues to add in more power for the exhaust combustion power stroke, which is also an exhaust. Yes, because it's immediately going to open up an exhaust while also intaking somewhere else and still creating compression. And okay, so then that's also exhaust being used to help intake, compress, and all the rest of it. That's why it's very efficient. So it's like all of it is being captured as efficiently as possible, I feel, for a very small little compact design for a motorcycle, which it's going to go off to the side. And there's still, it's going to have to expand because it got compressed, kind of slightly. Really, it's like that exhaust is losing energy and like we have to shrink it. But then it's like we're going to expand it into this. And it's like, this is where it's like, this is a big fan blade, not a turbo. We're not using that for anything. This is a fan blade that's going to be turned into essentially helping the plasma and or whatever you want it to be used for. For me, it's definitely more of a baffle system that is meant to help design once it gets up to slightly after it's it's what is it idle RPM. Thank you. The idle RPM. It's like, oh, it's trying to create this version of a vacuum kind of thing, but it's just not flowing fast enough. It hasn't hit that point. And so like now, then it's like, oh, it gets up, it creates a little bit of a vacuum, it improves flow rates for the exhaust, and so back pressure is reduced, and as a result, I gain, as it continues to go up to its maximum RPM, a degree of efficiency for the exhaust, because there's less back pressure, and so my intake is easier, my exhaust is easier, and everything's a little bit more efficient. Not to extreme hyper, oh my gosh, what the fuck, levels, but like, it's good, it's better, it's whatever's better, right? And I still get some amount of energy from it, and it helps reduce the, sound, because it's going to take that sound into the vacuum. So it's like, it's a good way to put this. It's kind of like a resonator. So it'll create a resonating frequency that goes and interacts consistently with the vacuum cavities that it creates. And so like that creates an active noise canceling, but then it's like still going to have pressure coming out, which is now in a fairly wide volume, which is now also a baritone low, very low frequency, which is good. You want low frequency, and it's now consistent as a sine wave instead of a pulse, kind of like a turbine, which now makes it much easier on the ears, and you still get rumbling, and there's a time when it is intaking and it is combusting, and so like it's always in between and then also doing it sort of thing. So you get the feeling of rumble and thrum and hum, okay, and you still get the sound, which gives you an indicator it's going and doing something, and then you still get the majority of that energy imparted into workable motion, okay, and then it also helps cool, because then it's still, well, it would have been really relatively hot exhaust, but now it's being cooled, so that's not bad. It also has a fairly efficient combustion and intake and so on cycle, which is what you're looking for. So, and then that thrust is like, okay, we're running very lean, and then we're running, allowing for the continuation of pressure in that now expanding, and so that thrust, it continues to keep, and then as a result of that, we're breaking down nitric oxides and carbon dioxides respectively. Well, not carbon dioxide, but carbon monoxides, that is. Right. And so then the fuel's still relatively lean, but because we continue to sustain a higher degree of heat and pressure, that helps with efficiency of the design, but also reduction of the negatives of a two-stroke or one-stroke or any of these engine piston designs. And so it should be cleaner. respectively, to a point. Again, it's nothing like a hydrogen engine, but it doesn't matter. It's cleaner than a standard motorcycle engine. In fact, it'll be even cleaner than a standard 4-stroke cycle engine. And in fact, even better if I were to add in like a plasmification, which I can technically do as well, if I wanted to set it up the right way with a version of, capture, secondary blade and counter-rotating blade, respectively, as it comes back in there, then I can compress, heat up as it's going to it, plasmify, re-expand, push in water, and get more out of that. So it can be just as efficient with that electricity energy into workable motion energy as you can be with a water, and gas combo. Why? Because the water breaks down, it decomposes into oxygen and hydrogen. So any carbons that weren't burnt were plasmified, and so plasma already, you're very close to the maximum temperature. When it's exhausted, that carbon dioxide will continue to be sustained, but it's under pressure. But then once plasma enters the situation, you then gain an advantage of removing those from the carbon. Okay, and there's still more oxygens and hydrogens to be had, and so it does its new exothermic, and then you can dump another bit of H2O, and that usually crashes it out, and exothermically allows for it to recombine, gaining new heat, but also more pressure because there's more stuff there, more density to the pressure, respectively. And then that also goes into your exhaust, spinning part, okay, which is connected to the other, whole turbine and balance and all the rest of it. Yeah, right. And as I respectively decline, it's not in any way going to be as good. It's like, okay, I'm trying to address your concerns when it comes down to any carbon monoxide, nitric oxides, and so on. Running lean usually means nitric oxides, but when you continuously burn, okay, which is what we're going to do, and that's essentially under pressure, it continually excites nitric oxides to be broken down, because there's a continuation of heat and a continuation of pressure, and carbon dioxide and carbon monoxide does not like to continue staying together. So exothermically, it will cool off, but then recombine and sustain its heat better over the length and duration of the fan blade profile. That is still going to change the exhaust force area, meaning like it imparts and creates power as it expands and pushes, but then is doing it in a slow manner to create a degree of measurable torque imparting, and then the rest of it is getting added into the hydraulic fluid recapture horsepower to torque converter for the exhaust manifold, which also gives it time. Which is like, it does not. And like, did you listen to anything we just said before this point? Okay. You have to understand where this is in terms of an exothermic reactivity. Okay. Exothermically, nitric oxide's not very stable. It's just not. But with the right heat and pressure, that instability will be turned into removed metastability. Okay? Because that's what it is. It's metastable. It's unstable, which means it's metastable. It seems like it's stable, but when you do the right thing, it's no longer connected. So nitrogens will recombine? No. All right. It's a good way to put this. You have hydrogen and carbon. You have nitrogen, you have some argon, and you have some oxygen, and that's it, practically. All right, so carbon dioxide is your main source, but there is many different versions of carbon that can be added to with oxygen. Okay, so as you add in more heat, as you burn, what you are doing also during this point in process is adding more excitation to carbon. Carbon does not like to bind like always when it's that hot, but you also have pressure. Yes, but pressure usually means more combination, meaning forced exothermic reactivity with things that normally wouldn't otherwise. Nitrogen and nitric oxide, not nitric dioxide, will become excited enough to loosely bind together. Nitrogen then decomposes and it will rip off the oxygen, allowing oxygen to combine with a carbon, which normally it wouldn't. So you have a carbon trioxide. And then because we're running lean and we have more nitrogen, typically in that side that has already bound to an oxygen, now it tries to combine loosely with itself with another oxygen. And now you have nitrogen dioxide, which is NOS, if you don't know, which explosively decomposes, which will then also form a measurable degree of increase of pressure as the oxygen is freed up. Any carbon that didn't have time to form is now going to form in the exhaust manifold with oxygen. But also, it tends to mean it forcefully makes carbon trioxides occur with gusto, really. And even carbon quad, or, fucking, this one's a bow tie. I love the bow tie version. It's like three carbons with two oxygens and or a third oxygen attached to one of them, with a loose connection typically happening with a nitrogen on average that will almost certainly remove itself from that situation very quickly and then separates into a freed oxygen and a carbon dioxide. Basically, nitrogen, because of this process, does not like to stick together with oxygen. Oxygen will try its pretty freaking hardest here to combine with anything because it has extra to give. And so nitrogen normally would be the thing that it would try and work with because it's more there. But as a result of the higher heat, nitrogen doesn't like to stick around, and there are now higher pressures and a greater degree of reactivity time for it to do this. And as a result, the greater degree of reactivity time and the exothermic reactivity going on removes nitrogen much more often, and it tries to attach to a carbon, which again tends to crash it out because that's losing energy, because it takes energy to do that, but it makes it denser. And then typically it'll break off as it goes through and cools off. And now because it's colder and there's not as much pressure, because there's an exhaust manifold which is capturing as much of its pressure as possible, tends to mean carbon dioxide's the really realistically main. There's still going to be nitric oxides, there's still going to be some carbon dioxide, but there's basically very little now that remain, and most of it's carbon dioxide in H2O to H3O and H3O2 and H2O3 and more, because typically that extra oxygen wants to go somewhere and almost inevitably breaks down again, helping sustain pressure because it's exothermic when it decomposes like that. It's all about that sustained pressure and heat over time. Now, I could be wrong, and you could be very, very, very right. Build the engine, do it, and test. Do it my way. Then we'll see. Otherwise, please be quiet and just try it out, maybe. Build it, that kind of thing. Now, we are going to go to the thing and all that stuff. So